Today we're going to be talking about how to draw the projections of the curve and then use those projections to sketch the curve. And in this particular problem, we've been given the vector equation r of t, where r is the vector and t is the parameter. So r is defined in terms of the parameter t. And the vector equation is defined as t sine t, 2 cosine t, where each of these are the three components of our vector equation. Now, when we talk about drawing projections, we're interested in three projections, and those are the projections of the curve onto the three coordinate planes. So let's just go ahead and draw an example of what we're talking about here. We have a three-dimensional coordinate system here, and if we follow the right-hand rule, we've got coordinate axes x, y, and z. We have three planes formed by our three coordinate axes. So if I draw a plane, if I fill in this plane is formed by the x-axis and the y-axis, so this is the xy coordinate plane. I also have the yz coordinate plane here, the yz coordinate plane, and I have the xz coordinate plane here. Now, what we're talking about when we say projections, we're talking about essentially the shadow of the graph onto each of these three coordinate planes. So if I have a curve here, let's say it's a simple curve, it's a parabola, and its vertex is here along the z-axis, and it comes out from the z-axis like this, and I'll do my best to draw this in 3 dimensions, but let's say I have this parabola, right? And it's the same parabola you would see in the xy coordinate plane, except it's raised up here along the z-axis. If I want to draw a shadow of this in the xy coordinate plane, that's going to look something like this, right? It's just the shadow of this curve, but in this xy coordinate plane. If I want to draw the shadow in the yz coordinate plane, I'm just pretending essentially that I'm shining a light from over here directly onto the graph, and I'm looking for the shadow underneath it. Well, if I'm going dead on here, the shadow is just going to be the straight line that comes out from the vertex along this yz coordinate plane. There's my shadow in the yz coordinate plane. And same thing here in the xz coordinate plane. If I'm shining my light from over here directly onto the top of this graph right here, and I'm looking for the shadow in my xz coordinate plane, that's going to look something like this. As my parabola extends higher and higher and higher, and the width of the parabola at the top of the graph is wider and wider and wider, I keep drawing the shadow, and the shadow would eventually extend all the way here. These would be the three projections of this parabola onto my three coordinate planes. Now, when it comes to identifying the projections of our vector function r of t, here's what we want to do. We want to treat each of these components of our vector function as parametric equations. So the x component of this vector function is t, so we say the parametric equation is x equals t. The y component is sine of t, so we say y equals sine of t. And the z component is 2 cosine t, so we say z is equal to 2 cosine of t. These are now parametric equations of our vector. When it comes to drawing the projection in our xy coordinate plane, we'll start with xy. We can draw a two-dimensional coordinate plane like this, where we have x and y. And in order to draw the projection on the xy coordinate plane, we need an equation for y in terms of x. So how do we do that? We have an equation for y here, but it's in terms of t, it's sine t. Well, we know that x is equal to t, so we can substitute x in for t and get from here y is equal to sine of x. Now we have an equation for y in terms of x, and that can be graphed on our xy coordinate plane. What we graph here will be the projection on the xy coordinate plane, the projection here in this plane. So if we graph y equals sine of x, here's roughly what it looks like, something like this, right? Where this point here, we'll label this as 2 pi, and this point here is pi. So there's our projection in the xy coordinate system. Now we need something in the xz coordinate system. That means we're going to need an equation for z in terms of x. So we're going to do the same thing again here. We have an equation for z in terms of t. We're going to substitute x in for t, and we're going to get the equation z is equal to 2 cosine of x. Now we have an equation for z in terms of x. We can graph this on an xz coordinate plane where we have x and z. 2 cosine of x is going to give us roughly something that looks like this, where our cosine curve is elongated vertically because we have this 2 multiplied by cosine of x. And if we label our points here, this is the point 0, 2. The curve starts at z equals 2 up here, goes down to pi at the bottom of the dip here, and then up to 2 pi at the top. So there's roughly our projection in the xz coordinate plane. Our last plane is the yz coordinate plane. So we're going to have the yz coordinate plane like this. And now we're going to need an equation for z in terms of y because we're looking in the yz coordinate plane. Well, we've got an equation here for z, but it's in terms of x. So what we can do is we can solve this equation here that's in terms of x and y. We can solve this equation for x in terms of y and then plug in that value here for x. So y sine of x, in order to solve it for x, we want to take the inverse sine function or the arcsine function, which we write sometimes as sine to the negative 1, of both sides. That'll cancel the sine on the right hand side, leaving us with only x, and we'll get here x is equal to arcsine of y. Now we have a value for x in terms of y. We can plug that into our equation for z in here for x, and our result will be z is equal to 2 times cosine of arcsine of y. And here's where our trigonometry comes into play. We have cosine of arcsine. This is sometimes written cosine of sine to the negative 1 of y, like this. Either way here, you can use the trigonometry of a right triangle to figure this out, but we've got a formula for it. When we take cosine of the inverse sine function, the result is the square root of 1 minus x squared. Keep in mind, though, that this x value in our formula comes directly from whatever's inside of our sine function right here. So in our case, we have y inside of our arcsine function, which means when we simplify cosine of arcsine of y, what we get here is z equals 2 times the square root of 1 minus y squared. Instead of pulling an x into here, we pull a y down into here, and we get 2 square root of 1 minus y squared. Now, in order to make this easier for us to graph, we can go ahead and square both sides. We'll get z squared is equal to 4 times 1 minus y squared. When we distribute the 4 across the 1 minus y squared, we'll get z squared is equal to 4 minus 4y squared. If I add 4y squared to both sides, I get 4y squared plus z squared is equal to 4. And then if I divide through both sides of my equation by 4, I get y squared plus z squared over 4 is equal to 1. And this is something we should recognize as the equation of an ellipse in standard form. In this case, essentially, we've got y squared over 1. Because the denominator under z is greater than the denominator under y, that means that our major axis is going to run here along the z-axis. Our minor axis is going to be along the y-axis. That means also that the length of our major axis is 4, so half of it is going to be 2. So we can draw essentially the ellipse here like this, and it's going to go off the screen a little bit, but something like this is my ellipse here, and I know that this value of z here is 2 because the square root of 4 is 2. I know this value is 1 because the square root of 1 right here is 1. So I know where my ellipse intersects the z-axis and the y-axis. I know that it's centered at the origin because I have here y squared and z squared instead of like y minus some k value squared plus z minus an L value squared. Because it's in standard form this way, I know I'm centered at the origin. So these are my 3 projections on the xy, xz, and yz coordinate planes. Now I need to put these together to draw a picture of the actual curve. Now I've found that translating projections into a 3-dimensional coordinate system to draw a picture of the actual curve takes a lot of practice and is really kind of tough to see, especially when you're first starting to sketch curves like this. But that's all it is just practice, and it'll get easier and easier to see these as you go. What I also recommend is if you have access to any kind of three-dimensional graphing software, or if you can graph these on your calculator and you can rotate the axes so you can take a look at each of the projections and then the curve itself, that'll help tune you into what sketching the graph from these kinds of projections is going to look like. So we've got our three-dimensional coordinate system, and I'm going to go ahead and draw in our coordinate planes. We just want to translate these projections into this three-dimensional coordinate system, and that should hopefully help us graph the actual curve. So I've got my system and my three planes. One thing I like to do before I start sketching my three-dimensional curve is go ahead and find the initial value of the parameter, or the parameter value at 0. If I've got parametric equations here, I like to set t equal to 0 and find kind of a starting point for my graph. So if I set t equal to 0, I get x equals 0. I get y equals sine of 0, or y equals 0. And I get z equals cosine of 0, which is 1, times 2 is 2, so I get z is equal to 2. That means I've got a starting point of 0, 0, 2. So my curve I'll go ahead and do in this color, but let's say that this is a value here of z equals 2. My curve is going to start right here in 3D space. Let's go ahead now, though, and draw our projections, or our shadows of our three-dimensional curve along our planes. So in the xy coordinate plane, which is this plane right here, xy coordinate plane, I have the curve coming up along this way, coming down through the x-axis at pi, and then coming back up to the x-axis at 2 pi. So remember, this value right here is pi, and we're going to call this 2 pi right here. The shadow in my xz coordinate plane, which remember is over here, my xz coordinate plane, is going to start at 2, so it's going to start right here at my initial point, and by the time it gets to 2 pi, it's going to come back up to 2. So if I kind of come parallel here to this plane, this is sort of my value of 2 on the other side. At 2 pi, it's going to come back up there. At pi, it's down at its deepest point here, so it's kind of going to look like this. I'll draw this one dotted so we can see the difference, but it's kind of going to look like this as a shadow on my xz coordinate plane. Then for my yz coordinate plane, which is up here connecting my y-axis to my z-axis, I've got this ellipse here. We'll go ahead and draw that in a different color just to help distinguish it. But notice here I'm going to start up at 2 and I'm going to come down to 1. I'll end up back at 2. Essentially, I have an ellipse that looks like this, something like this, and it's going to come down here. And there's my projection in the YZ coordinate plane. So how do I put all of this together? Well, I really just want to start at my initial point, which I've marked here in blue, and figure out where I'm going. If I look here in my XY coordinate plane, I'm going to see that from 0 here, I'm going to start moving out in this direction because my shadow moves out in this direction here. So I'm going to start moving out in this positive direction of the y-axis. If I look at my YZ plane, same thing. I'm moving out in the positive direction of the y-axis, but I'm also coming down a little bit. And then if I look at my XZ plane here, it just shows me starting to fall gradually until I get down here to pi. So if I start graphing this, I know I'm coming out in the positive direction of the y-axis. I'm coming out in the positive direction and I'm starting to fall because my shadow in the XZ plane tells me that. But eventually here, when I get out to this point right here, notice that my curve in three-dimensional space is going to start moving back in the negative direction along the x-axis. It's going to start moving back this way. So I want to start wrapping it back. I know based on my shadow in the YZ plane that it's going to start curving up again, and it's going to keep doing this sort of oval shape because my shadow is a perfect oval. So I know it's going to keep doing an oval shape like this. And it's just really here in intervals of 2 pi, which I can tell from my shadow on the XZ plane. So really it's just going to look something like this. I'm going to come back here and it's just going to wrap around. And if I come up this way, eventually I'm going to wrap around like this, and I'm going to start seeing my curve trace this sort of cylindrical three-dimensional shape. Now if I want to wrap this around a cylinder, because I said it was going to trace this cylindrical shape, it's going to look like this, trace this cylinder, and the cylinder is going to be like this. I can trace it through this curve that I drew so that I can see how the curve wraps around my cylinder. like so. And then I just want to show the perspective here of my cylinder, but I can see how this blue curve is wrapping around the edge of this cylindrical three-dimensional shape. Like I said, one thing you can do also is if you have a three-dimensional graphing tool, you can graph it maybe on a calculator or in a CAS. Let's take a look at what that looks like for a second. I've gone ahead and graphed our parametric equations in a graphing tool like this, and you can see here our graph sort of wrapping around the cylinder like we talked about. Here's my x-axis right here, here's my y-axis, and this is my vertical z-axis. Now remember the projections we talked about. If I turn my axis so that I'm looking at the xy coordinate plane, here's my xy coordinate plane here on the floor. If I turn it so I can see my xy coordinate plane here, I get a view of the shadow in my xy coordinate plane, which is that y equals sine x curve that we talked about. Now if I bring it back to where it was, this is x, y, and z, and I want a shadow in my xz coordinate plane, that's this plane right here, x and z, right there, and I can see my 2 cosine of x curve oscillating back and forth like that. If I want my yz shadow, I can just turn it this way. Here's y-axis and z-axis, and I can see this creating an oval as it circles out along the x-axis as we come further and further in the positive direction of the x-axis. And then if I just put it back in perspective here, I can see how it wraps around the x-axis like this. So that's how you draw the projections of a vector function defined by parametric equations, and then use those projections to draw your curve in three-dimensional space.